So, now we switch to a connected but relatively different case. Ah, sorry, I forgot. Let me go back just 1 second to the Fokker-Planck equation. So I told you that the Fokker-Planck equation is something like this. dw by dt equals to minus d by dz of a d1 of z and t w of z and t plus d2 by dz squared of d2 of z and t w of z and t, okay? Which can also be put in this form, and now you know what it is, minus d by dz j of z and t, where if you factor out one of the derivatives, what is left inside is j. I told you that this equation includes in itself the Liouville equation. The Liouville equation, which is for a deterministic process, is what stops here. If you go back and compare, you will see that it is the same thing. Okay? The Liouville equation is the case in which d2 equals 0. d2 is what arises from the stochastic part of the equation. So you don't have d2, which is the square of g, and g is the part that multiplies the noise. So if you don't have the noise, you have a deterministic evolution, and probabilities of deterministic evolutions are determined by the Liouville equation. Okay? So in that equation in which I wrote v dot equals minus gamma d plus gamma, apart from coefficients, okay? If you set gamma to 0, you have a deterministic process. But this process is very simple. It has a very simple solution. It has an exponential decay of the velocity. But it can also be treated probabilistically, because I can give a certain distribution of initial conditions. So you will have probabilities also in a deterministic process, which is what we did. And who decides how probability evolves? The Liouville equation. If you switch on a simple stochasticity, like many of you know, a Wiener process, then you have an extra diffusion term. Let me tell you, I already told some of you who came to my room, okay, that these kind of things are used, for instance, these days in artificial intelligence, okay, to learn how to reconstruct images and so on. Okay? And people have always considered diffusion processes easy, because it is true, they are easy. And now they realize that deterministic dynamics can also be beneficial. And like Boltzmann would say is one almost regrets to have to die before the answer is given. O immodest mortal, be your satisfaction in watching the shifting of the battle. Okay, so who lives, we'll see. It's not important. to have the final answer to all your questions. Enjoy the process. Okay? And he was using the language of a man of end of 1800s, beginning of 1900s. Today, perhaps we would use different words, but the meaning is that one. O immodest mortal. You are mortal, and still you are immodest. You want to know more than you are entitled to. Okay, take it easy. Enjoy. So about use of deterministic or stochastic processes in artificial intelligence, maybe I don't get to see what is the end of the story. Or maybe I do. Who knows? Now, related to the issue of dynamics and probabilities, which at this point, we don't care if they are produced by deterministic processes or by stochastic processes, because we have seen that they are connected. Okay? Related to that, there is at the very beginning the notion of ergodicity. Now, as I told you in the first hour, the beginning of the first hour, we haven't even started to scratch the surface of the subjects that I'm illustrating to you. But it is better to know that there is a surface that could be scratched than not to know that the surface is there. So I will do the same thing with ergodic theory, because ergodic theory is a huge subject by itself. It arises in physics, in the field of statistical mechanics, thanks to Boltzmann. Then it gets developed, it gets different terms in the hands of Maxwell, and finally Gibbs makes it something for the mortals. Okay? Through Gibbs, the subject becomes better and better known. Because unlike Boltzmann, who used to speak in a very complicated fashion, very hard to follow, Gibbs is very linear in his ways of reasoning. Okay? So, anyway, ergodicity arises with Boltzmann within the field of statistical mechanics. What did he want to do? He wanted to describe the evolution of a gas intended not as a continuum, but as an assembly of molecules. Things are very different in our understanding. Of course, this air is made of molecules, but if I could visualize it, I would see a continuum where there are no molecules. Look at the water. Today we don't have the glass of water that I can use to show, but the same thing. You look at the water, you see that there is space is all filled. There are no holes within the water. But if water is made of molecules, then it is more holes than, what is the opposite of holes? And then it is more the empty part than the full part. Okay? Emptiness is more than what is occupied. Water is in a denser state than air. In air, the occupied volume is practically zero. Okay? And we will see, hopefully, when I finish with the Boltzmann equation, what I mean mathematically. Okay? So what was the idea? The idea was that, say you have a container, and this container is divided into parts. And on one side of the container you have the molecules of your gas. Now, when Boltzmann was speaking about this, people did not know whether molecules existed or not. Okay? There were people who believed that they existed, people who believed that they were only a mathematical fiction. And there was big fight. That is the question about which Boltzmann said, oh, in modus mortal, don't expect to have all answers. Okay? Do atoms exist? You need something? Yeah. Do atoms exist or don't they? You know, the interesting thing, tragic in some sense, is that Boltzmann died in the very same years when the existence of atoms had finally been proven. Okay? So there is a beautiful book by an Italian writer. It is in English. It is a biography of Boltzmann. And the subtitle is The Man Who Trusted Atoms. So he trusted atoms when the greatest scientists of the time, Oswald, Mach, they would say, no, look, atoms are a good mathematical trick, but in reality, matter is a continuum. And Boltzmann, no, it's not a mathematical trick. But then he himself was aware of that, okay? And he gave a speech shortly before he died, in which he said, maybe one day my theory will be proven as wrong. And the idea of matter as a continuum will be acknowledged as the real substance of things. Okay? One regrets that has to die before the question is settled. Okay? What I told you earlier. Now, he died committing suicide in Italy. He used to come to the north of Italy, Trieste, near to the ICTP, where some of you have been or know about it. He committed suicide because he was under very serious depression for many years. Some people say that he committed suicide because he was frustrated with the fact that people didn't want to accept his theory. But Cercignani, the author of this book, says, no, I mean, he was under depression for many years. So he went to Italy on a holiday with one of his daughters. And then they found him hanging. So he never knew that Einstein's theory of the Brownian motion would provide the proof that atoms exist. Okay? Einstein's theory of 1905, and Boltzmann dies in 1906. Before they do the experiment in 1908, in which they prove Einstein's theory to be right, and Einstein's theory was inspired, of course, by Boltzmann. Okay? So, as I said to some of you at the break, take life easy. Okay? Enjoy the beauty. Enjoy the beauty. Even when things don't go well, there is beauty. Okay? So I like to tell this story about Boltzmann because it tells a lot about human beings, but also about science, about our field. Okay? Our field doesn't arise from people without feelings. It arises from real people. Okay? They're not just in the books. They were people who suffered and who rejoiced. So, what happens if this is not a continuum, but is a bunch of molecules? If I dig a hole in this wall, And experience tells us the molecules will move out and fill the whole container. Oh, thank you. I did not mean to have a glass of water. But since it is here, I drink. So he wanted to have a theory of a deterministic process, because the molecules are supposed to follow deterministic rules. They bounce off each other. Okay? And continue in their motion forever. But their equations of motion are time, reversal, invariant. Which means that if you can go from molecules all on the left side to molecules half and half distributed, sooner or later you go back to being in only half of the volume. This is related to what Zermelo, the famous mathematician Zermelo, used a theorem by Poincaré, which I mentioned briefly in my first lecture, Poincaré recurrence theorem. Zermelo told Boltzmann, look, you cannot have what you describe. You cannot have that a gas goes from left to fill the whole thing and remain like that if your molecules obey time, reversal, invariant equations of motion, because Poincaré proves that you will go back. So your model of atoms doesn't work. There was another objection to Boltzmann. So this was raised by Zermelo. Okay, the one of the axiom, very famous mathematician, very smart. The other was raised by Le Schmidt. Who was an old friend of Boltzmann, a physicist rather than a mathematician. And he also had one objection to what Boltzmann was saying, because he said, look, if instead of this bunch of molecules, say with certain velocities, you take the same bunch of molecules with the opposite velocities, which is possible, rather than going to fill the whole container, you will squeeze even more. And that is also allowed. It's only a choice of initial conditions. So Boltzmann was to face this quite challenging objections that they go by the name of paradoxes, Zermelo paradox and Le Schmidt paradox. And then basically he creates the field of statistical mechanics, which recently a very, very important scientist, one of the top neuroscientists in the world, Jim Hudspeth from Rockefeller University, that I'm going to visit next month. He told me, if you know statistical mechanics, he's not a physicist, he's not a mathematician, but he knows a lot of both. If you know statistical mechanics, you know everything. I told him, Jim, he's 80 years old. Jim, knowing statistical mechanics, because he wanted to compliment me, okay? He's not knowing everything. He's having some tools that everybody wants to use. So Boltzmann, in practice, although there were previous things, okay, Bernoulli, Fourier, the Italian Cantoni, many others who had already done a lot in the direction of connecting statistics and mechanics. But Boltzmann, at this point, makes it plain okay, a deterministic process which is chaotic in some sense, okay, will behave as an irreversible process even if all the actors involved obey time reversal invariance equations of motion. Okay? You can see that these days, after a lot of fighting and a lot of study and so on, these things can be justified by simple pictures. So suppose you have a billiard table with two balls in it. And these balls are moving, bouncing off the walls. Now, for a short time, you can neglect friction. But also, these days, you can do experiments with what are called cold atoms, a very microscopic level, just by manipulating atoms. Now, I give you this picture at the time t1, and I give you this other picture at the time t2. Can you tell me which picture has been taken first? Is t1 larger or smaller than t2? What do you think? You can guess whatever you like. You don't do any mortal sin. You will be spared if you don't get the right answer. Or what should you tell me in response to my question? I'm asking a fair question. Again?
T1 is larger.
You say that T1 is larger, so we have an ordering like this. So this comes first and this comes after. Any other guesses? Again? Anything is possible. This is another guess. Now you see, time reversal invariance means what you just said. That you could have had the initial velocities oriented like this, and then this comes first and this comes later. Or you could have had a different, the initial velocity to be like this, and then this comes before that. And it makes no difference for a time reversible mechanics. Is the other answer incorrect? No, it is not incorrect because whoever told us the molecules have to obey time reversal invariant equations? We don't know. It is our assumption. And only in time and repeating experiences and calculations, we have found that it is a good mathematical representation of what we have seen so far to tell the molecules that constitute a gas obey time reversal invariant equations. But if tomorrow Professor Sivaraji does an experiment that disproves this statement, then we change the theory. Okay? So I'm not telling you that this answer is wrong. I'm telling you that within our mathematical models, this and this are equivalent. But these are mathematical models. Is that reality? That's a different question. Now I'll give you two different pictures. And now again, this is T1 and this is T2. And what I tell you is that you go from one to the other through a spontaneous process. Now, I'm not the one who takes the balls and puts them here, there, there, okay? I just give an initial impulse to the balls, and now ask you if T1 is larger or smaller than T2. What would you say? The equations of motion are the same. Okay? Still balls bouncing off each other. What would you say? T1 is larger or smaller than T2? No, nobody wants to answer. Again? T2 is larger. Why do you say that T2 is larger?
I think it's a fluid, right? It's a fluid, so the particle will not be so close for a long time. It will scatter. Go away from it.
So this, because we don't have too much time, so I have to continue. You see, it's enough I kick one of the balls, and I will have, okay? And then they will spread. While, if I want to go from here to here, I have to aim so exceedingly accurately each single ball. This, the second experiment, I think that even with today's technology is not possible. Even with present-day technology. Because the dynamics are chaotic. Okay? And then here you have an exponential of 15 times something. Or an accuracy that has to be e to minus 15 and something else. It goes beyond our technological abilities, okay? So, in this case, it is fairly natural to think that T1 is smaller than T2. Then again, we can always argue that if you are good enough, you could do the opposite, yes. But suppose that you watch a movie in which particles go from this situation to this, and another movie in which particles go from this to this, I can assure you that you will find going from here to here fairly unnatural. Why? If the equations of motion are the same, time reversal invariant, why? This is the thing which Boltzmann, developing ergodic theory, had to fight somehow. Why? The difference is statistical. Here there are many balls, and here there are few. So, with the same deterministic equations, you can have something that looks like a stochastic process, because this goes from order to disordered, from order to random, or a very deterministic process that allows you to put a camera on a comet. The laws are the same, but the effect is totally different. Now, that thing is paradigmatic of all standard things that we have. Going from here to here would be if you have a hot and a cold body, that heat goes from the cold body to the hot body. You never see that in your daily life. But these days, we see it in nanotechnologies, for instance. These days, we can have that heat goes the opposite way. Why? Because we go down to small systems in which going forward or going backward in time makes no difference. Okay? So, this to give you an idea of where we are. Then ergodic theory comes out of this physical description and becomes a very thick branch of mathematics that is called ergodic theory, and that combines measure theory and dynamical systems, which is what I have tried to do in my course. Okay? So, after so much talk, let's write something. that looks more precise. So to define ergodicity, we have to do this. We have to have a dynamical system, which means a manifold, M, but in the end, a phase space where things move. We need to have some dynamics on this M, continuous or discrete. And then we need to have an invariant measure, mu. Invariant means, as we said at this point quite long ago, means that the probability that it represents does not change under the application of the dynamics. Okay? Things are moved around in phase space, but the probability remains distributed in the same way. And now there are 4 properties of a dynamical system like that can be proven to be equivalent. From one you prove the other, from one you prove the second, from the second you prove the third, from the third you prove the fourth, from the fourth you prove the first. Okay? Now, if you want a good book about this stuff, the mathematical theory, then that is by Riccardo Magnet. But there are many. A Brazilian who died fairly young. So the first property, we call it E1. And it says this: for every integrable function, O integrable with respect to that measure. For every integrable function O from M to R, you have that time averages and phase space averages are the same. We have that O bar of x, which is equal to limit t goes to infinity 1 over t integral from 0 to t of O computed along a trajectory starting at x is equal to the expected value with respect to mu. Now, I think we already did this question in the first class. Now, this thing cannot be true in general for all x, because this depends on x, and this does not depend on x. So we have to say mu almost every x in M. Okay? This is the first property, E1. Second property. It says that for every measurable set in our sigma algebra, we have that the residence time fraction of a trajectory that starts at x is equal to mu of A. Again, here there is no dependence on x. So we have to say mu almost every x, where tau A is equal to limit t to infinity of 1 over t integral from 0 to t of the characteristic function chi A along the trajectory ds. So what is this? This is the average amount of time that you spend inside the set A. The average amount of time that you spend inside the set A has to be equal to the measure of A, with an exception set of 0 measure. No, I'm sorry, maybe I drank too much water this morning. Can you wait a second? Now, property 3, E3. There are no non-trivial non-trivial integrals of motion which integrals of motion or constants of motion are those quantities that they don't change along a trajectory. Okay? It's like if you go to a mountain, they are like level sets. If you know, rather than climbing the mountain, you go around and remain at the same altitude, then the altitude is a constant of motion. It does not change. Of course, it's not constant because you are going around. Okay? But the altitude remains the same. So there are no non-trivial integrals of motion. It means that all those that exist are trivial. Trivial means that they are constants in the sense of Lebesgue, apart from a set of 0 measure. Okay? So, in formula is this. If O phi t x equals O of x for all t and mu almost every x, O integrable. Okay, it means L1, okay? Or integrable. So if you have this situation, then you have that O of x is a constant Ko independent of x apart from this for the set of zero measure. Mu almost every x. So if you are a constant of motion, if you are an integral of motion, then you are a constant. In the sense of Lebesgue, you are a constant. You belong to the equivalence classes of all functions that are equal apart the set of zero measure. E4 says this is a bit more mathematically abstract, but it is useful for proofs of theorems. E4 says that the dynamical system is metrically indecomposable. Is metrically indecomposable, which means if A is an invariant set equals phi t A for all t, then either mu of A equals 1 or mu of A equals 0. It is called indecomposable, okay, because you see that any point in A has to remain within A, and every point outside has to remain outside. And so A, a set of full probability 1, is explored by single trajectory. And that single trajectory keeps it together. It is indecomposable. If you break it, you break also the path of some trajectory. Okay? Now, lemma. EI are equivalent. Okay? Which means that if you can prove the validity of one, then all the others hold. Or if you assume that one holds, then all the other follows. Some of these equivalences are fairly quick to be seen, because I told you many times of the density of simple functions in L1 space. So the first two, okay, get the equivalence using that property, because with characteristic functions, linear combinations of them, you can build any function of L1 arbitrarily close in the L1 norm. So going from here, you can go up there by a density argument, density in L1. Okay? And you continue like that. The usual thing, I think, is to go E1 implies E2, which implies E3, and then E4, I don't remember well the sequence. I have to think. Maybe it is in my notes, which I wrote, but I don't remember always everything, okay? This is the notion of ergodicity. Now, if you combine E3, E3, yes, if you combine E3 with E1, you will understand why Boltzmann found that this notion was suitable for his problem. Okay? Because suppose that there are no non-trivial integrals of motion. Then, if you want a probability measure that is invariant and that has got a density, I like the other one better. If I want to have d mu of x equal a certain probability density f of x dx, then f is a function. I want it to be, if that is to be invariant, then f should not change in time. Then it will end up within the integrals of motion. But then, well, here the reasoning is a little longer, but then, if that is an integral of motion, and the dynamics are Hamiltonian, as we said earlier, which implies that there is no contraction or expansion of volumes, then the consequence through E3 is that f is constant almost mu almost everywhere, which means the uniform distribution. Okay, so if your system happens to be ergodic, and it is ergodic if one of these properties is verified, okay? Definition. M phi mu is ergodic if EI holds, whichever it is. Okay? So if your dynamics happens to be ergodic and your dynamics are Hamiltonian, then there is only a distribution of probability that is invariant, and it is the uniform one. Okay? And so your gas has to be distributed uniformly over the space. And it is invariant and it doesn't go back. Okay? This is the notion of ergodicity. Some of you already had in mind this notion. I tell you that there are many theorems related to this notion. I also tell you that if you give me a generic dynamical system, typically it's pretty hard to prove that it is ergodic. Even if it is ergodic, it is pretty hard to prove that it is. Of course, there are cases in which you can prove it, but typically they refer to very simple dynamics. So let me show you one kind of ergodic dynamics. suppose we are in the case in which the invariant probability is precisely the Lebesgue measure, dx. Then this E2, what does it mean? It means that every trajectory will spend some time in any open set of positive measure. So if my measure is dx, it means that if I take any open set, places anywhere you like, your trajectory will go through it and will spend a certain fraction of time in that set that is equal to the measure of that set. So that means that trajectories are dense in the phase space. Now I'll give you one example. And the example is this. You take a phase space which is a square that could be seen as a torus that has been cut. Okay, so it produces periodic boundary conditions. And I take a certain number of points in a certain region. And then I say that these points move with constant speed, with constant velocity along space. Okay? So they move parallel to each other. Now, because of periodic boundaries, when the points go out this way, they come back this other way. And they continue. Now, if the angle that trajectories make with respect to the horizontal are rational with respect to pi, if alpha is equal to the ratio of two integers times pi, all trajectories will eventually come back to where they started, and you will be on a periodic orbit. Because you go few times around one direction and you close in that direction, maybe you have not closed in the other one, but there is a common multiple of these two that take you back in both directions, both in x and y. And so you come back and you close your trajectory. You are on a periodic orbit. So if alpha is like this, you are not ergodic, because a trajectory doesn't go everywhere. It goes only along the points of the periodic orbit. But if alpha is not rational with respect to pi, then there is no multiple of return times that is common both to x and y. So trajectories don't close. But if trajectories don't close and you cut a line through this space, you will see that when they go out, they come back at a certain distance from each other. Then they go out. They cannot return to the point where they started, so they come back closer. They come back to another point. Okay? And they cover this by steps of a fixed distance because the slope is fixed. So if they do this, they have to accumulate everywhere in space. And so trajectories will fill densely this segment. And then, of course, every segment will be filled densely. Trajectories will be dense. So simple dynamics like this are ergodic. If that angle is like that. But this property was not considered good enough because the points don't spread to fill the space. They don't spread to fill the space. So people have invented another notion that is stronger than ergodicity that is called mixing. I give you the definition of mixing and then I stop as I was required by Professor Sivaraj. And mixing, unlike ergodicity, but similarly, is defined by two properties. Which are these. If I find them, otherwise I go by heart. Well, no. Let me give you the main theorem of ergodicity. It is this one. And then mixing, I tell you something in the afternoon. Now, if I go back, you see that the first property is the equality of time averages and phase space averages. Let's see what can be proven. This theorem dates back to 1932, I think. It's due to Birkhoff, who made von Neumann very angry because von Neumann had the chance to tell Birkhoff that he had in mind something, a proof in L2, and Birkhoff developed for L1, and then it became his theorem. Okay? So it is this. What we can prove is this, is Birkhoff ergodic theorem. Birkhoff ergodic theorem. What does it say? It says that take a dynamical system m phi mu. I give you in the notes also the proof of this theorem. It's fairly long, okay? But it is nice. It's very instructive. Take a dynamical system like that. Then you have this, A. For f in L1 of m and mu, what you have is that time averages exist mu almost every x. B. F in LP of m mu, okay, with 1 less or equal than p less than infinity, implies that not only the time average exists, but f time average belongs to LP. Now, you remember that the time average depends on the initial condition, x. Okay? So it is a function. C. It also converges in the norm. Lim, say for discrete dynamics, lim n goes to infinity of the p norm of f bar minus some 1 over n, some in I that goes from 0 to n minus 1 of f composed with the dynamics phi I, this norm goes to 0. So the time average exists. It is an LP function, and the partial sums, or partial integrals if you are in a continuum, converge in the P norm. Moreover, the time average is a constant of motion. F bar phi x equals f bar of x. Because if you move forward some steps, you still have to average over an infinite amount of steps, so it will make no difference. That part of the theorem is easy to prove. C, if f is in LP of m and mu, always with 1 less or equal than p less than infinity, then unfortunately what you can prove is not good enough. Then what you have is that the phase space average integral over m of f d mu, which is the phase space average, okay, what I called the E mu of f, I think, okay, is equal to integral over m of f bar d mu, not equal to f bar. Okay? So it is a very weak result compared to what Boltzmann wanted. And you cannot go much beyond this, although it is old, unless you choose very special dynamical systems that can be proven to really be ergodic in the sense that I have shown before. So life is hard. But there would be many ways out. But I think we have to leave that for when you are older, and I'm older too. For today, this is enough. Thank you. Sorry, you will be busy while I go to lunch. Then I come back. I hope you forgive me.